We continue our discussion of facility layout with a short study of assembly lines. An assembly line is a setup where sub-assemblies or parts are added sequentially to a system being built by workstations, while the system is transported from workstation to workstation in some manner. It is normally assumed that all workstations have equal processing times. But there are different types of assembly lines, depending on the method of material handling, the line arrangement, how the process is paced, does it handle one or several products, the workstation setup, and the extent of the line. Typical products assembled on assembly lines includes toys, labor-saving devices, cars, aeroplanes, weapons, garden equipment, clothing, and many electronic components, products. We can say without fear of refutation that most products with many parts are assembled on assembly lines. Assembly lines need to be balanced to ensure that all workstations have an equal processing time. This has implications for the layout of the line. Sometimes the design of workstations and the number of workstations are impacted. The most frequently used assembly line is based on some kind of moving conveyor that carries the item being built from workstation to workstation. Workstation operations include either adding parts or performing assembly. A workstation may perform one or more tasks which add up to the workstation time. The assembly line balancing problem is thus one of dividing all assembly work between workstations such that they all have equal workloads. That is, a workstation may have less work than the standard workstation time, but not more. The goal is to minimize the workstation idle time across all workstations. Achieving line balance is made difficult by the design and technologies involved. These require a certain order of assembly, which then constitutes a precedence relationship. The process of line balancing is not difficult. We will first present the method and then illustrate it by example. It consists of the following 7 steps. Step 1. Set up a precedence relationship diagram, using circles for the individual tasks and arrows to determine the order of task execution. Step 2. Determine the workstation cycle time by dividing the total production time per day by the required number of units to be produced by day. Step 3. Determine the theoretical minimum number of workstations, NT, required to satisfy the workstation cycle time constraint. It is given by the sum of all task times divided by the cycle time. This number is rounded up to the next higher integer. Step 4. Select rules for task assignment, that is the primary rule, and tie breaking, the secondary rule. Step 5. Assign the task to workstations, starting with workstation 1, filling its capacity as much as possible, and then progressing to workstation 2, and so on. Step 6. Calculate the efficiency of the balance by dividing the sum of the task times by the product of the number of workstations and the workstation cycle time. Step 7. If the result is not satisfactory, change the decision rules and rebalance. Let us look at an example to illustrate the method. This example has this Model J wagon which is to be assembled on a conveyor belt. 500 wagons are required per day. Production time per day is 420 minutes, and the assembly steps and times for the wagon are given in Exhibit 6A9. The assignment is then to find the balance that minimizes the number of workstations subject to cycle time and precedence constraints. Here we have the 11 tasks that must be performed in assembling the Model J wagon. For each, a task time is listed, as well as a description and the precedence between tasks. The total building time for a wagon is 195 seconds. The first of our 7 steps is to draw the precedence diagram from the information in the last column of Exhibit 6A9. The result is shown in Exhibit 6A10. Calculate the workstation cycle time. We have to convert the 420 minutes production time per day to seconds, as that is our unit of time. Thus 420 minutes give 25,200 seconds divided by 500 wagons required per day to give a workstation cycle time of 50.4 seconds. Calculate the theoretical minimum number of workstations by dividing the total time for the assembly of a wagon, 195 seconds, by the workstation cycle time found in this previous step. This gives 3.87, which we round up to 4. Thus a minimum of 4 workstations will be required. Choose the task assignment rules. Some rules have proven themselves to be better than others. One of the very good rules for our purpose is to first assign tasks that have many followers. So this is our first rule. Consequently, we order our tasks in the order of the number of tasks following them, from large to small. See the table. Task A has the most followers, which is 6, followed by B and D that has 5 and so forth. The secondary rule chosen is to assign tasks in the order of their task times, from most to least. So let us associate tasks to workstations. First, we start with task A, which has the greatest number of follower tasks. See our table on the right. We allocate task A to workstation 1. Station 1 now has a total task time of 45 seconds, which means that it has 5.4 seconds less than the cycle time of 50.4 seconds. But there are no other tasks that can be performed during that time. The shortest remaining task is task J, which is 8 seconds long, apart from the fact that it cannot follow on task A. Then for the next workstation, we can allocate either task B or D, according to our primary rule. But our secondary rule favors task D as it has the longest task time of the two. Thus task D is selected, with the consequence that workstation 2 has 0.4 seconds idle time. For workstation 3, we now have task B according to our first rule, with tasks C and E as next candidates. Both have 4 followers, which makes E the logical choice in terms of our second rule. Next will then be task C, which still leaves 15.4 seconds idle time for the workstation. This must be chosen from tasks F, G, H or I according to our primary rule. All 4 of these have 12 seconds of work content, and we choose the first one, which is F. This leads to workstation 3 having 3.4 seconds idle time, and so forth for the workstation 4 and 5. Workstation 5 is the consequence of too much remaining idle time for the first 4 workstations remaining. You will remember that the theoretical minimum number of workstations was 4. Let us complete the task assignments specified in Exhibit 6A, 11A to form Workstation 1, Workstation 2, and so forth, until all tasks are assigned. The results is shown in Exhibit 6A, 11B. So let us calculate the efficiency of the solution. Divide the total time required to build a wagon, 195 seconds, by the total time available for 5 workstations at 50.4 seconds per workstation. This gives us an efficiency of 77%. Step 7. This is very inefficient with 23% or 57 seconds idle time. The question now becomes whether a better balance is possible. In this case, the answer is yes. Try balancing that line with rule B and breaking the rules with rule A. This will give you a feasible 4-station balance. This then ends session 4C on assembly lines.